All right. Hello, everyone. Let's get started. Well, beer is waiting, right? Cold beer. Everyone is here for the beer. Sorry to be the last of the day, and hopefully I can entertain you a little bit. This talk is about Hbase versions. The title 96. When I submitted the talk, that was the current version. It's 98 now, so I'm sort of extended this and called this 96 plus. I'm with Cloudera, for those who don't know me. I see a lot of familiar faces here, so it's more like a gathering of friends, it feels like. I'm doing consulting there. I'm also working on Hbase as much as I can. So I'm a committer for Hbase, and I also wrote the Hbase book. So if anyone who doesn't have a copy yet, if you want to have a signed copy of the book, you can go to our booth, and if you find me there as well, I'm happy to sign it, so you can pick up a book. And you have my contact details. If you have any questions, please let me know. Right, so this talk is about the versions, what happened in Hbase. Who of you have been to the talk from Ines and Devaraj just before, the other Hbase talk? A few? Okay, just a few. So this gives you an overview of what happened, what happened in the last couple of years in Hbase, and where are we heading to. Ines and Devaraj were really in the code. They gave you a talk on, if you watch that back on video, about these features that I'm also going to mention. I won't go into those details, but I will point them out so you can go back and watch their talk on recording and see what happened. So first thing that I try to do is just give you an idea of how things sort of evolve in Hbase, and I think it's quite interesting. Early on, if you look to the left, you will see there's Hbase 90 that was released early 2011 and has been around for quite some time. So it took like nearly a year for the release of 92. So about a year until 92 was released. Half a year later, we started with 94, but 94, on the other hand, if you have a look there, sort of lasts much longer. It still lasts, it's still ongoing. That is, I'd say, it can be attributed to the release manager, which is Lars Hofhansel from Salesforce. He's really driving this forward. So he keeps on, he's using 94, I guess, in production for Salesforce, and so he's keeping on adding what is interesting. I just get less and less what he adds, but he's keeping on releasing those versions, and they're up to like 0.16 on that one. That's like unheard of. All the other ones, they stop after a couple of iterations. Then sometimes in Hbase you will find an odd number. So you see on the left-hand side 90 here, you see 92, 94, and all of a sudden there's a 95. Sometimes you will see this. These are developer versions. I'm not sure when we do that. Sometimes we just say, let's branch and let's do a developer version. Not sure why. But sometimes we don't. Sometimes we go straight from sort of like a release version to a release version. That's very similar to what you see in a Linux kernel, which has odd and even numbers for that same reason. We try to keep with that, but don't bet on it. So it's just a convention that we're currently using. So 95 we started 95 here in April 2013 and added more and more features to it. And eventually it turned into 96, which is the release version, and the production version of that same. So all of the changes in 95 went straight into 96, and we kept developing then 96 onwards with point releases to have all of the features that are needed and added them as we went ahead. So that is ongoing. So I'm not really sure, because what happened here now is, again, another release manager took over. Every major version has a different release manager. And the release manager for 98, which is Andy Pertel, he is here as well. He's with Intel. They added cell-level security, which is a big feature to bring us on par with, if you heard of Accumulo. We wanted to have the same feature set in Hbase. So they only added this particular feature and a couple of others around security into that release. And they said, okay, 96 is done. Let's get all of these things in that we're already working on, and let's do a 98 real quick. And that's, again, if you see like as a year in the early days, and all of a sudden here from like that 96 release in October, we have in February, we already have 98 out. That's why I got caught unawares. Well, I knew it's going to come, but when I lodged that talk, handed in my application, I was sure it's going to happen, but I wasn't sure when. So we're at 98 right now. The other thing is, and I want to say thanks to Lars over there, we counted overnight the JIRAs and tried to figure out how many real issues have been closed. You could even go further and really try to value those JIRAs. What are the important ones? How many really important features have been added? That's a whole different exercise. Maybe someone here interested in machine learning could start that as a project and somehow group important JIRAs, maybe by the number of discussions or so. I'm not sure, notes, comments in the JIRAs, I'm not sure. But if you look at the numbers, 90 has like 1,300, 92, 800, and then it keeps on going. You can see the 96, which was the 94 plus 96, keep this in mind, I fold them together. They have quite a lot of updates, and 98 had 1,400. That's what we say on the blog post as well. That's not entirely true. So we went ahead and said, let's look at all of the features that have been added uniquely to a version, so that those JIRAs that appear in, say, 96, but also 98, don't count them towards 98, only count them to where they appear first, just seeing what are unique features. And that's how it looks like now, which is much more sensible, because now we can say we really only 96 added a huge amount of 1,500, but 98 only added 400 new ones. Like, this is much smaller than before. You think it's like there's a lot in there, but it's because all of the important JIRAs from the previous version went in there as well. Then for the book, just as your information, I targeted 92 when I wrote the book in beginning to mid of 2010. Basically around that timeline in June, I had to hand in a stop. I had to say, that's it, I can't track this anymore, I have to hand in the book. This is one commit here, that's the way the commits look like. That's the date, that's the release, or the revision number in the repository. And really, as you saw earlier, beginning of 2012, 92 was released. And in between, if you do the math, if you run that command, between the two revisions, I'm lacking 800 commits. And 800 commits is a lot. There can be a lot of small things, but also there can be quite a few bigger things. So I'm trailing by 800 commits. So some things in my book aren't really that current anymore. And for example, there's one big commit that's like changing the entire file format. So I'm describing a file format in my book, which is the first file format. We will see this in a second. But really, in the 92 that came out, you had the choice of two. Like, we would typically opt for the new file format. So it's not unimportant, but I'm working on an update. Let's go through these different versions, and that's sort of the core of the talk, to give you an idea of what happened. Interesting thing is, or if you're interested in it, I put the JIRA numbers next to it, so if you get that talk afterwards and you find any of these features interesting, maybe for your work, there's the JIRA number. You can just search this on Google and have a read through the JIRA and see if that actually applies to you. Those that I listed, I went through them all. There's a couple of that I found interesting. This is also one of those things with JIRA. You read the description, it sounds great. You read through the actual JIRA, and you realize it's not doing what it said it's going to do. It's like there's some description saying, I fixed the world, and in the end they say, I don't think I can, and then they just close this thing as invalid or something. Those you would filter out, but there's sometimes they promise more than they actually do. So please be careful to read this. So in this version, as I said, about 600 issues addressed, 811 total in that timeline. So about 800 new features went in between 90 and 92. One thing that is important, I think, is a new logo. No one noticed that, I guess, and it is rightly so. I don't like it. But anyhow, H5 v2, I talk about this in a second. What also went in are performance optimizations. 92 also added things like distributed log splitting. This is important if you ever run a Hbase cluster in production and you have something crashing, for example, then it's important that things are recovering as quickly as possible. And one of the things that have to happen if a server crashes is that before you can reopen data to serve that data, you have to replay the binary logs of that data that has not been yet persisted in the stores. So we have a binary log that we keep writing to, and eventually we rewrite the data, and you have that data persisted, so you don't have to do anything. But typically under load, when this cluster is busy, you build up a little bit of backlog in that binary file or this binary log. So when a server crashes, you have to have a splitting. That was previously done in 90 by the master. The master had to split all of the log files that are accumulated. Splitting here means separating the content so they can be applied to the regions that the edits belong to. They got all thrown into one single one. That's just the architecture of the way the things work. And that was not good because you had like one single server that had to do all of the work before anyone else could move along. Bad idea. So the distributed log splitting helps you orchestrating that across all of the different servers. Now, the master, all it has to do is it has to say, you region server 1, you pass this file and break it up. Region server 2, you take this file, and so on and so forth. And once they have done, it makes sure that all of them are separated, and it waits for them to finish. It's more like an orchestrator or conductor waiting for these things to happen. So that's important. It helps speed up recovery. And I'll get back to this in a second. There's more to come in later versions. We also have improved in this version a bit on the master UI. You will see there's a bit more information there. 92 adds, for example, progress in certain actions that happen behind the scenes. In the past with 90, you would fly blind. You would have maybe some log entries that would tell you something is happening or something started, but this is for the hardcore people to like look at logs and figuring out things out, what's currently working, what isn't working. Worst thing with log entries is that it might only log the start but not the end. So you know it did something or might still do something, but you don't really have a progress. So we added these things to the master that you can see the compaction progress, regions in transition, that's when they move between servers, and also tasks. Tasks are in general things that the server has to do, and that framework is being used later on for other stuff that we see in the next version. Another feature that went in that I also didn't document in my book, for example, is the slow query metrics. We had always this trouble that sometimes you would issue a query and it would not perform as you would expect it performs, like in the millisecond range, and you're wondering what's going on. You can actually then say, enable this log, and you can see how many of those happen, and then somehow start tracing back what's going on. That's the first step to sort of somehow watching what's going on. And again, newer versions, you will see this in a second, have more of this. We will see this as repeating. We're trying to get better at telling you what the system is actually doing. The big thing, and that's the sort of the name of 92, and I put this on the second page here because it has diminished a bit, is coprocessors. Coprocessors is a way of plugging in functionality on the server side. So you can write code, that is jar codes, that you compile them into jars, load them into the server, and have them execute. And I'll go into that in a second. I'll go into this in a second. The other interesting thing that went into 92 is the off-heap cache. There's a SlapCache that is off-heap, and again, I'll go into that one in a second. Online table schema changes, you can change. Previously, you could not change without stopping and starting the cluster or the server. Now, or disabling the table and re-enabling the table. Now you can do this. It means you're changing something. For example, you enable compression on the column family, and it would reopen this for you in the background. It's not like it's actually just putting this into place. It actually has to do some grind in the background, but it does that for you. So you're just issuing the command, and if it can, it will roll over and reopen all of the regions one after the other in the background to apply the changes. But keep in mind, for example, if you would enable compression, that's not something that would happen automatically. You would have to run like a major compaction or wait for new files to be created. Those will be compressed. So just saying that some of these features, even if there is online table schema changes, like adding another column family, these are immediate. But changing some attributes, they might not be immediate. You have to wait for that. We also changed the region size here from like a very small a quarter gig to an entire gig. We actually changed this later on again, but very early versions of Hadoop were, although big data, we're talking big data typically, were quite small in terms of defaults. It's not really useful. So we upped this number because the system was more capable of handling larger regions. We added Hadoop support. Snappy compression went in. For those who don't know, Snappy is that Apache license compressor library from Google. That's the same thing they're using in Bigtable, which is the granddaddy of Hbase. So that's what all is modeled after. So we're using the same compression as Google does in this case. And other smaller improvements went in. For example, what is interesting is the second last, keep the last version for time to live. We had this, in Hbase we had a time to live that you can configure on the column family level. You can say, everything in this column family, keep this for, I don't know, say 30 days, right? That's fine. The problem is that after 30 days, and if you don't add anything new to it, everything is gone. So if you just add to a column, columns into a column family, they get, as you have configured it, after 30 days, they get kicked out. The problem is sometimes you want to have at least the last updated value. Like you don't want to throw everything out. You want to at least have what was written last. Doesn't matter how old it is. And that's what went into 92. So you can actually configure, do not delete the last version of everything. So at least you have something that is archived and sits there, and you can read something from there without saying, well, that is gone now. I don't know what his name is. He hasn't changed his name in 30 days, right? So it's customer XYZ, but I don't know what his name is. Bad idea. Then other things like multi-threaded compactions. That's something that Facebook actually added. Facebook, we heard, I don't know if for those of you who heard that talk earlier, they really heavily invested in like engineering and engineering on those components that they're using. And Hbase is one of the big components they're using, for example, in Facebook messaging, in their Insight products or product. So all of these trying to optimize Hbase as much as possible is one of their major goals. And they're tweaking and tuning and following their track over the years. Although they have diverged from the mainstream, they have their own branch, but we can see what they're doing. They're publishing what they're doing. You will see that they have tuned it to a level that most of us might not even have to go to, but we can learn from it. We can see if we get there, we have to like watch out for certain things, like tuning it a certain way or other things. And one of the things that they did is they realized, for example, that sometimes if you have files on your file system that need in a background operation need to be compacted, sometimes it makes sense to prioritize smaller ones over larger ones. Because if you have a large one, that backs up all of the small ones because you only had one thread doing the compactions. Now you're hitting a very large column family, you had to wait for it to do its background writes, right? And then nothing else would happen. But then you had these other column families who would write a lot of small data, and you could not catch up eventually because you get more and more data, you have to do them one after the other, and you have to wait for them, for the big one to finish. And they just built a large compaction pool and a small compaction pool. And you can actually tweak the size of each. So now you have thread pools for different sizes, and within each size you have multiple threads. So you can actually tune these things. So keep an eye on that. If you ever go into a system that is heavily loaded, you might want to tune how the compaction algorithm works. If you have too many threads, obviously you have more background operation. If you have not enough, you might not catch up with your changes. So let's have a quick look at the file format. So we drill into one or two of the items that I listed earlier. So here we have 90 has previously laid out the files like this. You see basically in the previous file format, in the H-file v1, H-file for Hbase file, this is what it's called. These are directly stored on HDFS. In the previous format, we had the data blocks here. The data blocks had a magic starter, that's just a byte, predefined set of bytes that indicate here starts a block. And then you have these key values, which are actually your column and the value of that column. And then you had some metadata blocks. They were optional. If you don't use metadata, they were empty. And then they had a trailer, and that trailer kept indexes into the file. So when you open up the file, you would read the trailer. This is a fixed size trailer here. With this trailer, you would know where the offsets are into the metadata index, the data index, and the file info. And then from there, you would say, if I need something from the data, over here, this data, with that data index, you could jump and read those blocks out of the file, right? In the new version, H-file 2, which I just missed, as I said earlier, so I must just miss this to document that, but I will certainly add that now. It splits up this organization of blocks. The problem was that if you use Bloom filters or if you use compression, where the blocks get typically smaller, eventually you had a problem that the indexes were quite large and you had to keep them in memory. You have to always read the trailer of the file and know where things are, and you had to cache them in memory. And that, with the number of files that you have and the size of the files, could get quite large. So to overcome this problem, Facebook implemented HFile v2, where they actually splitting up on only having a root index, and the root index would then point to other indexes in between. So they had like leaf indexes, bloom filter indexes in between. So data blocks could be in between here somewhere and are interspersed with the indexes. You would only read a small major index, the root index, and if you need to look up a certain block, you would read that part, that leaf index, and from there you would then find which block has your data. So it's one more hop to read, but you only have to keep a limited amount of structures in memory for every file. So it sort of is a trade-off that way. Then what is also interesting is that the block header, like the header that is in this block file that I saw earlier, is not just a magic anymore, but this block header has a block type, has a compressed size and an uncompressed size, so we can do effective seeking forward, because now we know how large a block is. In the past we had to consult the index. We don't have to do this anymore. If we have a start of a block, we can jump to the other blocks real quick without going back to the index. And this is interesting here, we have the offset of the previous block. So if you have multiple data blocks, you could also find where other data is backwards. This is being used, and I'll pick this up in a minute, in a newer version. And then you have the data as well. On the other hand, I mentioned coprocessors is the other big thing that we added. Coprocessors, I said, is code that you can run, you program against an interface, build a jar file, and then you can upload this to the server, and then you can deploy functionality into the server where the data resides. So you can run little programs that do something directly at the region level. That sounds great, because it's like where the data is. You don't have to do any RPCs. You can just say go, and then the server-side code, which is already loaded, would do its work and return, for example, an aggregate. That's where it's built for. So Google uses that to build the machine translation models they use in Google Translate that way. That's one of the places where they're using that. The way this works is that whenever you have an operation, when the client comes in, you basically have first system coprocessors, and then you have user coprocessors chaining together. This is very much like what you see in HTTP, like in Jetty or in all of these web servers, where you have like filters you can chain. The first one can react. It can actually say stop here. No other filter will have an access to the data or the call. You can stop the whole thing, or you can just pass it through, say I don't care, or next one, do your work. And then they go through, and then they go backwards from here to the user. So it's basically, there's a different region. It's two regions, both load the same code. Or you can then use an RPC call to talk to these things. So for example, you could plug a code file, or some code into the region server that tracks, say, your usage, how many calls you do. I mean, say you have metrics for that too, but if you want to track some operation or some aggregate on the server side, you could deploy a coprocessor and then using an RPC call to get the current value back. That's very much what you see in Storm, for example, which aggregates constantly, and then you have an RPC that you can use to call and trigger and query the current value. So you could build something like an event processing here as well on a very high level. It's not like the same thing, but you could do something similar. And so you could have either, there's a couple of ways to invoke this. You can actually call this, but you would call it over here. You can deploy an RPC. There's a custom RPC then, and you can say, give me the row counter, for example, and it would return a value. So these are the two things to our coprocessors. What I mentioned earlier, my concern is here just that coprocessors are not code-weaved, they're not protected. Just be careful what you load into the server. So this is why we sort of toned down the message that we actually have coprocessor. It was the big thing with 92, but in practice it might be not the best idea. You might do something wrong and take the entire cluster down. So just be careful. We now say coprocessors is more something for system developers who know what they're doing, like a driver programmer who knows what they're doing, and if something breaks, you know where to point to because he wrote this bit. Not just everyone should plug anything in Hbase, just as a warning. The other thing that went in, this was the last thing I wanted to mention, is the SlapCash, which is interesting. We added an off-heap block cache that allows us, using Java Neo's byte buffer, direct byte buffer, to not load all of the data that we get from disk into Java heap, Because those who have used any Java and under stress, you do not want to run in garbage collection pauses, and eventually you typically do, because your heap fragments, and if that happens, then eventually you have to stop the world, rewrite the memory, and then free the world again. And if that happens, you can't respond to any request, which gives you spikes in latency, and eventually sometimes even servers being considered dead. And that's something you don't want to have happen. This should help you here, because what you do is you shrink the heap size. You run a region server in, say, 4 gigs of heap, total, Java heap. And then you use the off-heap cache, the SlapCache, to do this all outside on main memory. It slows down a bit, but if you look at the numbers, this is from, I always put the sources down here. You can read up on that one where this is coming from. But they did some testing, and if you look at the memstore, which is purely in L1 cache, directly in the Java code, this is the fastest. If you do 10 threads, for example, this is the number of operations. You can see this is the fastest. The LIU block cache only is already quite fast. That's the normal, this is a cache that we have. This is the in-memory store for writes. But if you use the SlapCache here, you can see it's not too bad, basically. It's it's a penalty. A bit of a penalty, obviously. But if you look at what the system cache is doing, the operating system cache, if you would just say, I disable caching, that's here basically the file system cache is much slower either. So if you compare this, it's basically there's a difference. So it's in between leaving it up to someone else and keeping it in memory. But it's a choice. If you have trouble with garbage collection, you might want to look into this. Right, next version, 94, that's called performance tuning. We have again, lots of issues there that have been fixed. 420 in the initial 94 release, and in the entire line, 94.1, 0.2, and so on. We have over 1,300 issues being fixed. This are lots of sort of subtle things. We can see here, for example, the read cache improvements, that we actually improve how we store data on a cache and how we retrieve it, how we seek in files. I don't want to go into these details, they bore you as well. But keep in mind, this version has looked at everything that moves and tried to find ways to improve it. Interesting is that when I heard this Facebook discussion this morning, they actually now debugging operating calls on the kernel level. They look at HDFS while it's having these little spikes, and they're finding that is an issue with these, for example, these stable pages that they had to tweak with. If you heard that this morning, interesting talk. But they really on this level now. This was a higher level where we had still in our realm we had issues. They are already going way down on saying, okay, we still have some tiny little peaks and spikes, and we need to get rid of those. And they're stooping down to that one and helping us finding them, which is an awesome effort. So here we added, for example, ways of better finding data. We don't have to read all of that by having trackers, what is being deleted. We don't have to seek around. Removing I/O, making things faster. Lazy seeks, for example, doesn't means we don't just proactively open all of the files or load from all of the files. We wait until it's being requested, and then we look into the files and load blocks. Also interesting, we are using now write-ahead log compression, so you can enable this in 94. That will help you taking off the load of the write-ahead log. Again, one of those things you should look into if you get into these performance areas. We also added an encoding, and I have something on this one, and improved the check that we have, like a Hbase FS check to repair things. We simplified region management, or region sizing. You can just start with one single region, and it proactively splits the regions faster in the beginning and slows down as you grow. This was in the past the problem. If you configured, say, 5 gigs of region size, you had to wait 5 gigs of data to land in a single server before you would split this into 2, and then had 2 servers to respond. If you had 10 servers and only one server would respond, that's not a cluster. That's a single server doing the work for you. This one would proactively split quicker and then slow down. Once it reaches all of the servers, it would slow down and not do this anymore, and then grow to the total size where it should grow to. Interesting thing for users. You also have improved API calls for transactional semantics, like an atomic put and delete in one call. You can just put something there and delete it depending on a condition. It just helps you getting around the fact that Hbase does not have any transactions. We backported snapshots into 94.6. So this one has snapshots already. If you want a snapshot, like an entire state of a table, for example, as of this version, you can do this. Atomic appends, you can send something to the server and just say, add it to a cell somewhere, I don't care what it is, add it and forget about it. So all of these things, again, help speed your application up. And a few other improvements. We also have more metrics. You can now track what's happening per column family. We have an interesting feature called multi-row local transactions. That's something whenever you discuss NoSQL solutions, the first thing you hear is typically there's no transactions, there's only row-level atomicity. That's not entirely true. With Hbase, you have a way of saying a couple of rows, consider them an entity, keep them together, don't split them, and then you can update these couple of rows atomically. So you can actually have multiple rows that you can update across rows, and that feature went into 94 and also needed a few other things, but it's all, for example, this pluggable split key policy, but it's all in there and you can use this. Operational help, like we had issues where sometimes Hbase was not aware what's in a region. It would balance the cluster out. So if you had, say, 5 servers, they all had 10 regions. But the problem is that one small table, which has, say, 3 or 5 regions, was located on a single region server. So when you talk to that table, you get no parallelization. You got only one server serving those 5 regions. And that's a bad idea, again, because you have no performance. This is this load balance regions by table and is also backported to 92. And further deprecation, and we have a canary test tool. Real quick on the block encoding, that you get some idea what that actually means. This is one of the interesting features. Block encoding means that we encode the keys of a key value pair. A key is really in Hbase is the row key. It's a timestamp, it's a column family name, it's the column name, and a type. So there's a couple of information. So if you have like a row called Joe Blogs, and in Joe Blogs you have email 15, that's the 15th email that he received, and you would have to store all of this as part with the email. So the email record would contain all of this information. That in certain use cases, if you have small values, means you have a lot of repetition of row keys. If you have a row, say, with 1,000 columns, you will store 1,000 times the row key on disk, and you would store 1,000 times the column family name on disk, right? And all of these things, this is lots of repetition. And the block encoding helps you taking this out. So that's basically there so that you can encode them, replication and repetitions are being extracted, and they stay like this. So you store them encoded, and then they get written to disk encoded, and then you might, on top of that, still compress the data. So that's something you can do on top. And here's an example that comes from this Jira. So they use like a 90-byte long key and only an 8-byte value. That's typically for a counter, if you do counter updates. And if you enable the encoding of the keys, the compression ratio is 92, like in 92 of the original. And then you have, if the total compression of the entire document is basically, or the entire store is 85%. If you then LZO the same data, the raw data, you get to sort of the same level as the total compression. So this total compression means, it's the encoded key and the original data, like the uncompressed data. And then if you do the combination, if you encode and LZO, you end up with a compression of 91. Sorry, from the other way around. So that's the reduction percentage. So this is the highest. If you then encode and compress, you get the highest compaction. How does it work? If you look at like this, for example, I mentioned every key value has all of this repetition in here. You can see here, this is qualifier 0, 1, n, 1, and so on and so forth. This is like row key. This is the first row key, the second row key, and the key length is here 24 bytes and 25, and you store this every single time. So this is no encoding means it's stored as is, and you need all of that space. With the prefix encoding, you're actually storing for the key only what changes. So this one is 24, as we saw before, and the next one is basically there's a prefix of 23 same characters of the one before. Then there's one change, which is the number 1, so 0 changes to 1, and this one to n, and so forth. You can see how this goes down from 24 to 1 only, right? So this like condenses all of these sort of overhead in the encoding. But as I said, it only works on the key. Then then there's another one, the diff encoding, which goes even further, which encodes not just this one, but also encodes the differences, for example, in timestamp. So you have the origin timestamp, and then you reduce this, and they use ints, like a variable length ints, to even bring this further down. So these ones will be just 1 byte or something to be stored, or 2 bytes or so. So this is a step on top of that. It is more complexity, so it takes a bit more hit, but it's still interesting if you have certain use cases. So in terms of penalty, the advantage is you can actually seek in these data structures. In anything that is compressed, you can't really seek. Here you can, so that's an interesting one. Then you can also, as in terms of penalty, it's slightly slower because you have to do some decoding when you read the data. So if you look at those, they have some numbers in their JIRA. If you're interested, it's maybe like a 10-20% hit, or say 10% hit I've seen for the decoding part. But everything goes much smaller, so you can read more in one go. So you get it back on the I/O side of things. Try this out. 96, we're moving on. 96, and it gets less and less. 98 has much less left. Has lots more issues. 96. Again, we improve stability. We improve the scalability. You can see those issues here. This time I don't go into details. That is stuff that Ines and Devaraj have talked about. So if you want to know more about that, that's what they're working on. So there is a talk they have given on, especially on this MTTR, mean time to recovery. That's a very interesting one. How we can make sure that if something happens to a region server, that we can recover real quick. If you ever get attacked in a NoSQL war, or whatever you call that, like a competitive situation where we get compared, like Hbase gets compared to another NoSQL solution, typically what comes up, people will say, yeah, but if a server crashes, I heard there's a couple of minutes before you can access the data again. That is not true anymore. With this version and onwards, it's down. You can, soon, with 98, you can take on writes immediately, so it will never stop. And the read side of things will be bring down to like the low second range, if in the future with read replicas even further down to nearly nothing. But then we buy into eventual consistency. There's also other stuff. We have health scripts that we can run now. We can check if the cluster is up and running. That helps. We switched everything to protobufs. The reason why this thing is called Singularity is because of that. Because now we can actually do rolling upgrades in the future. Because now every protocol, every store that we store, every information that we persist is protobuf versioned, which means we can now, a newer version of like 96.1, 98, can read 96 and say, yep, I can read it. I have a new field I added when I write mine, but I can read the older information. So that's important to roll forward. We have namespace support. You can actually have namespaces that separate data, more improvement on metrics, and add more internals. Interesting for those who know, root is gone. We never needed them really. Well, nice to know you, but it's gone. We only have a meta table left. So in terms of system table, as of 96, root is gone. It's out of the door. We're only using one meta table, one system table. We also have improved on the encoding side. We now have a tree. There's different pronunciation. I think it's tree data block encoding that further helps you condense data for a certain use case. Again, read the issue if you want to know if you can use this in your system. We have rologs that you can use. We removed the rologs. We had the rologs in the past. That wasn't a good idea. We removed them because there were like issues. For example, if you had a log on data and the server would crash, the log was gone. Not a good idea. So there's no logging anymore, which no one really should have used anyways. It's gone. We improved on compaction and flush. Again, this is something that Devaraj and Ines have talked about. You can follow up on that one in their talk when reviewing the video. And there's operational and more operational help, like online region merging is now possible. You can, if once you had too many regions and you want to bring them back down to a smaller number, now we can do this. As of 96, you can merge these regions. That wasn't possible in the past. We get a new type of cache, not just that off-heap cache. Now we have a bucket cache, which allows you to store a cache on SSDs, which is an interesting use case. So instead of having expensive memory to store it in, you can have now a, whatever, say, half a tera SSD and use this as a cache, which is an interesting proposition. This was contributed by the Fusion IO guys, so interesting use case as well. New UI, we had a new logo earlier, now we have a new UI, it's Bootstrap based, and oh no, this is a repetition here. So mean time to recovery, that's the last thing I want to talk about here, is that it's really about being faster. Again, I'll point you to the talk of the other guys. But the important takeaway is every single phase that happens between being able to access data again, we're addressing in this sort of major effort. And so we're looking at how quickly can we detect that the server is gone. Once we know the server is gone, how quickly can we recover the data? And all of these steps, again, please look at the other video, or if you have been there, it will give you more information on that one. Right. Nearly at the end, 98, I said, only adds cell-level security as the major feature. Also has server-side encryption. That sort of complements the cell-level security. We have improved, we have a reverse scanner. The reverse scanner is exactly what I mentioned earlier, what uses the information in the file to know what the previous block is. The reverse scanner takes care of that, so that you can actually now reverse in the file. So what previously you could only search forward in Hbase, now you can search backwards. And you can iterate over snapshot files and so on and so forth. So this is all just improving on these things. A new file format again, because for the cell level security we have to store more information. So we now have a H5E3. We improved on the ACLs and other things that we needed for the security. The way this works, and this is the end of this here, is we need labels. For example, if you had, for example, this sort of set of privileges, confidential, secret, and so forth, you could combine them into what is allowed to see. For example, you could say they have to be secret and top secret, but you can't be a probationary level. So if someone with probationary authorization comes in, he would not be able to see that particular cell. You at every cell in Hbase, every value that you store, you can attach these labels, and then when someone tries to read them, they get evaluated, and you can control who's seeing, who can see it, and who can't. Right, that's the end. What is happening in the future? There is basically not much written in stone. We're waiting also, we need your feedback. I'm hoping we get like a 1.0 soon. What is being worked on is further improvement, consolidate the master, locate the meta with the master, bringing down more of anything that is currently costing us more time, trying to optimize further. Bootstrap or streamline the architecture of Hbase. You will see Hbase being more reliable, faster, and having feature-wise only, I think, minimal additions. It's more that we're getting faster again and more reliable. I think that's the primary goal for 1.0, and then we can release this. Any questions? Yes?
When we are talking about Coprocessor, we have troubles to replace the code currently.
Yes.
It's 96. Is it possible to do something, or is there any recommendation for best practice?
Replace coprocessor code.
Yeah.
So the question is, how could you update code that is being deployed to a server? No, you can't. You have to restart the server. It's one of those things I hate the most. This is also why I'm saying this is not really for sort of constant change. You would test it in your local environment and deploy it once, and then with a release, you would update the coprocessor. It's just unfortunate. We talked about different ways of having a container system there that would have a container that would load these things, and then you can unload them. But anyone who does Java, class loader, is just hell. And so we don't really have the answer, right? Niels and I, we were talking about this earlier, right? So maybe we can, one thing that I suggested is that we maybe have a generic coprocessor, and then you have little lambdas now that you can send to the server and they execute over there. We just talked about this with filters, it's the same thing. And no, we don't have anything, and it's not being addressed, no one's tackling this. Please, if you have ideas, I would love that someone helps us out. Any other questions? If the question is, are any comparison benchmarks between 94 and 96? I do believe there are, but they are sort of like strewn across the mailing list. I think Jean-Marc, if you search for him, he has a rig set up and he's testing them typically against them, and they published some numbers there. There were some regressions initially, and they discovered them and addressed them, so I don't know from the top of my head what the difference is. Because keep in mind, it's feature dependent, so if you don't switch on any of the, say encoding, you get the same performance because not much has changed. But if you start switching on encoding and then compression changes and whatever, that probably gives you the extra gain on top of that. But it's use case dependent. Yes? The question is when do we, you mean Stripe compactions or like the 98? When do we make Stripe compactions available to the customers? You can't hold me to that. I'm just saying that C5 is coming out very soon, the next couple of days, which is CDH5, which has... I just pressed the button 5 minutes ago, so I wasn't sure if it's already there or not. Kidding. So that is there, which has 96 version of it. 98 will go into the next point release. So 5.1 is supposed to have that. Work has been started. We might have to push it out if something fails. But the plan is for 98, so that for you to be available in a quarter, like in 3 months. Any other questions? All right. Yeah. Hey, I can see. Yeah. Yeah. The question is if anyone is looking at what Facebook is doing and if we're backporting it to the mainstream. Definitely. All of the Facebook guys are good friends with our Hbase engineers, so they're exchanging these things. And the interesting part is a lot of that stuff that they did is on a very low level, like even HDFS and even lower. So we have to figure out how we put this into even our distribution and switch things on and off or whatever. So we're definitely tracking that. Whatever they do, we get as well, I'm sure. And I personally will take care of that if I have to, because what I heard there is like great stuff, and this will come. The problem is to track all of these things. If you have more questions, I'm at the booth. As I said, come by and get a signed copy if you want to have it. You don't have to. Don't be intimidated. You can just walk by and just ask questions too. And otherwise, I wish you fun with Hbase. Thank you.